Okay, so this lecture is going to be on repetition. I've been advertising this for a couple of weeks now, but finally get into it. This is when things really start getting interesting. We add this tool to your tool belt, and it enables the ability to create some really interesting projects at this point. So a lot of this, I want to give a little bit of a warning up front. I'm not generally going to focus primarily as I'm teaching about repetition on what's available in Python, because Python is a little bit more limited than other languages. Different languages do repetition different ways and have different features available. All of our assignments obviously are going to be still using Python in here, but assuming that you'll use this as a launching point to go on and possibly take other programming languages, I want to not leave you ignorant about the other forms of repetition that are out there that you're going to come across. So just be aware. I'm going to try to teach the idea completely, not just limit it to what you can do with Python. There's also some interesting things you can do in Python that are not easily available in other languages too. So it's not like Python. I'm not complaining about Python when I say this. It's just I want to teach about repetition, and Python lets me illustrate some of that and doesn't let me illustrate other parts of it. So just keep that in mind. So what we're going to try to cover tonight is the different forms of repetition that we have available to us. Keep in mind, this uses those Boolean expressions that we've been talking about, when we were doing the if statements, if and a Boolean expression. So you can kind of read those Boolean expressions and add the is true or is false at the end of it, because that's actually what we're asking. If I say if variable name, I'm basically saying if variable name is true. If I say while condition, I'm saying while condition is true. So just kind of keep that in mind when we're talking about Boolean expressions. You have that little bit of semantics to keep in mind. You can nest these things, just like with nested if statements. You can have loops within loops within loops. I'm not going to get too crazy about that tonight. We can look at other examples that require nested loops in the future, but I'm going to try to limit it for tonight. In general, out of tonight's lecture, we want to be able to look at a problem, like one of the kinds of problems that we've been assigning, and we want to look at that and pick out the parts of it that involve repetition, and then be able to create the pseudocode, create the flowchart, create the Python that implements that repetition pattern in the problem that we're looking at. Yeah, and then we'll talk about how we flowchart it and how to do Python. Python has range that you can loop over, which is kind of unique to Python. Other languages have similar things, but that's kind of a unique thing to point out in Python, so we'll go over that too. So when we talk about different kinds of repetition patterns, there's some terminology that you have to kind of grok. Counter controlled, sentinel control, range controlled. We have this terminology, definite versus indefinite versus infinite repetition, and then pre-test and post-test. And there's also mid-test or mid-loop testing. Python doesn't support the post-test. It kind of supports the mid-loop test, so we'll talk about that too. But like I said, other languages support all of these, so we want to talk about them. I'm going to take a little bit of a long way around the barn here for a minute, so apologies. But, sometimes, when I was in my early days trying to figure out how the computer actually does all this stuff, how does it actually work? How does it know to take our instructions and actually implement it? Because, inside these boxes, there's a bunch of circuitry, right? A bunch of little silicon chips that are actually doing what we're asking it to do. If you ever have wondered how it actually does that, I'm going to kind of take a sidestep here for a minute and try to explain some of that, how it helped me to make sense of it. Has anybody heard of surface tension before? The idea of surface tension, okay? You know, if you had science class, it probably came up at some point. Um, let's see if I can show this little video that I wanted to show. Sometimes the school computers let me do this, and sometimes they don't. Go get my link somewhere else. I'm a human. I'm supposed to be able to win this argument. I'm going to win this argument. There we go. Okay, so there's this little video that talks about surface tension. It's not very long, just a couple of minutes. But, you know, the general idea is you have this cup and it's mostly full of water to the top level. You know, if you calculated the dimensions of the cup, you can figure out exactly how many milliliters of water it's designed to hold. But then you keep adding more. So they've got this cup full, and then they start adding pennies. And we're illustrating the surface tension because the water level keeps going up above the top of the cup. Well, what's holding it? Why isn't it running over? And it's that surface tension holding onto it, right? And they're actually illustrating it there too. Once in a while, you can tell when they put the penny up there that it actually grabs a little bit of the water. And if they dropped it from like an inch high, it would cause enough ripples that it would break the surface tension and let the water flow over because the variation in the pressures. So they keep doing it and they speed it up and they speed it up and they speed it up. And finally, they get to a point where they add the last penny and it can't hold that surface tension anymore. And, well, look how many pennies they're adding. How much volume still will go in the cup, even though it's already full.
What's adhesion?
And here we go, the last one, and then bloop, then it goes over the edge. Okay, so you've had that in science class, apologies, but that's just the little analogy that I wanted to start with to help this analogy along. Okay, yeah, so at some point the tension's broken, the adhesion is not enough to keep the water in the cup, and it goes over. So extending that analogy a little bit further, and I may be abusing some of this a little bit, but like I said, this is just how it helps me figure out what's going on inside the silicon that's making this work. I love this. Wouldn't you have loved to be the guy back in 1906 that invented something called the thermionic triode? Doesn't that sound completely Star Trek? I mean, to be famous for inventing the thermionic triode, that would just be so cool. Also, the fact that his last name's DeForest, and DeForest Kelly was one of the guys in Star Trek, just seems to fit. I just think that's really cool. But anyway, this goes clear back to 1906. So Edison, the guy that, you know, we're familiar with living in this area, he had, you know, done some experimentation and he observed, there's this really weird thing where I can use this really small amount of current to control a much larger flow of current, okay? So then in 1939, this guy starts experimenting with these vacuum tubes and he figures out how to combine them together to create this computer. Of course, back then they thought of it as, oh, this is a computing machine. Nowadays, in our modern computers, we would probably call that an arithmetic logic unit because it, you know, for it to be what we call a computer, it's got to have other input peripherals, output peripherals, memory, and those kind of things. So today we probably just call this the ALU, which is a very small portion of the silicon inside a modern processor. It's the ALU, the arithmetic logic unit. But the cool thing about this is this tube is able to implement something that allows, they have this little piece of metal in there. And what they found was if they have a positive and a negative wire and they stick them inside this vacuum tube, there's no electricity flowing across them. But if they heat up this panel and they put a little bit of current on it, then all of a sudden, at some point, all of the current starts flowing from the positive terminal to the negative terminal. So then they get current flow based on introducing this little bit of current to this heated panel. And so they put that inside this vacuum tube, sucked all the air out of it, and they had a whole bunch of these. Anybody else play with vacuum tubes in your life? I guess I'm old enough. See, I can remember when, in our house, my parents finally bought a color TV. I think it was when the Chiefs were in the first Super Bowl. My dad went out and bought a color TV to have at home so they could watch the Chiefs playing the Super Bowl on a color TV. But it was about the size of this table. It was a big console television. And if you opened up the back of it and looked in there, it was glowing. It had all of these little vacuum tubes. No silicon, nothing elegant, no integrated circuits back then. It was all vacuum tubes. Well, that did go out once or twice during my childhood. And what my dad would do, he would turn the TV on and he would look at which tubes weren't glowing. Like, okay, well, those are the ones that we suspect, right? So we turn it off and we pull all of those tubes out and we take them to the grocery store. And you walk in the grocery store and, where you would typically see the ATM and the stamp machine and stuff like that today, they had just this little box sitting there, looked like an arcade machine. And you'd walk up there and it had all of these sockets of different sizes and shapes and number of pins. And you'd look at the number on your tube and you'd find the slot that fits into, and you'd stick it into there and you'd hit the test button and it would either say yes or no, whether that tube was good or bad. If it was bad, then you'd throw it in the trash and you'd look down in the little shelf and you'd try to find one of the same number. Oh, there's one in the box, and you'd go buy it. Then you'd bring it home and stick that back in there, cross your fingers, turn the power on, and hopefully your TV came on. So that's how you would repair your television back then, is you just replace the bad vacuum tube. So I guess I'm old enough that I had to do that a couple of times with my dad doing it and me watching him, basically. Anyway, so vacuum tubes were fun. And then we got integrated circuits and silicon, and the rest is history. So moving on to the later part of the 20th century, we came up with this thing called a transistor. And the transistor, all of these little silicon bits, every one of them was made to replace some kind of a vacuum tube initially. So they wanted solid state electronics that would replace the more physical, glowy implementation of it inside a vacuum tube. So in the 1920s, this guy named Julius Lilienfeld, not as near as cool of a Star Trek-y name, but we'll give him a pass, I guess. But he filed a patent for this thing called a field effect transistor. Not as cool as the thermionic triode, but okay. With a name like Julius Lilienfeld, maybe we can give him a break on that too. But he never did build a prototype. He just thought, hey, this would be a really cool idea, drew up some stuff, filed a patent for it, and then never realized it. So then this guy named Muhammad Attallah in 57. So from the 20s all the way up to 1957, nobody does anything with this. And then finally, this guy came up with the metal oxide semiconductor field effect transistor, or we commonly know those as MOSFETs. If you, in the last 20 years, played an electric guitar and you really wanted a vacuum tube-based amplifier because they have that authentic, old, cool, classic sound, then it probably had some MOSFETs in it, you know, but that's what that is basically. It's a silicon implementation of the vacuum tube that does the same thing, that lets us control a larger flow with a smaller current. Okay, so this is kind of how it works. You have the source, they call it a source, and a drain. So if you imagine those being like plumbing, pipes, right? You have current that's trying to get in here, but the resistance, just like with that cup full of water, the resistance is too high for it to get out here to the drain and for current to flow across that circuit. But you start adding pennies through the gate, you have a little bit of voltage, a little bit more voltage, a little bit more voltage, and eventually, boom, all the current starts flowing through that. Okay, so that's how I got that analogy. I thought that was really cool. Technology like that, you can see the N's and the P's. It's called an NPN transistor, just because that's how they make the silicon. They dope the silicon with impurities that makes it behave the way they want it to. But all transistors will have that same pattern. They have a source and a drain and a gate. And if you apply current to the gate, it causes the current to flow. Well, that's really cool and revolutionary for us computer programmers, because it lets us implement the notion of an and condition. If I have current here, but not here, nothing happens. If I have current here, but not here, nothing happens. But if I have current on both of them, on this and this, boom, the light bulb comes on over here. So we have an and circuit inside a transistor. So transistors were completely revolutionary to modern society. So as soon as this guy, well, I mean, you can see it went from the thermionic triode to Edison, to this Julius Lilienfeld, to Muhammad Attallah. All of these people contributed to advances on this thing until, boom, we get the NPN transistor. It gets, you know, codified inside silicon. Then they figure out how to get tens of thousands of these transistors on a head of a pin, and we get Intel CPUs. So that's how we got it. Yeah, so on-off modes, but you turn up and, you know, you saturate. Saturation is another way to think of this too. As soon as you saturate the silicon with that gate, then boom, it opens up the floodgates and the current can flow through there. I just think that's really cool. So then, you know, they start representing it graphically. You know, this is like a electronic person's version of a flow chart, right? We do flow charts, they do schematics. But you can see all these little symbols in here. You can start to recognize them. Those are the transistors. They have 3 pins, right? You have the source, the sink, and the gate. And if you apply current to 2 of them, it goes out the 3rd one. That's all it is. And then they come up with all these different variations of it by wiring it together, but it's just variations of the same circuit, just flipped around backwards and combined with other ones. If you want to know how all that works, you can go read about that in a solid state electronics book. But anyway, I think it's pretty cool.
Yeah, it is. It goes into the whole current whole complete circuit.
Yeah, and I mean, we don't have to think about that consciously, but I think it's pretty cool. When I first started programming professionally, I was programming in assembler language. And here's another concept I can kind of analogize for you. In assembler language, everything is extremely primitive. You don't have while keywords. You don't have if statements. You don't have these fancy, you know, 3-line long conditional expressions. Everything is one small operation at a time. And if you want to do something complicated, you have to build it up with 50 or 60 assembler statements to do the same thing. Everything's brute force. So there's no loops. So the way things work in assembly language is you execute some instructions to move things around in memory, and some of these operations cause flags to be turned on and off. Then later you have branch instructions, and the branch instructions will go one direction if the flag is on, or stay where they're at if the branch is off. And by go somewhere in assembler, there's this thing called the instruction pointer. You know how we've been desk checking our code? And like we write a bunch of code on the board and I stick my finger next to the instruction that I'm executing. That's my virtual or physical, I guess, instruction pointer. Well, in a program, an assembly program, you have a value called the instruction pointer. It points at the next instruction. So every time it executes an instruction, it goes to the next one and keeps updating that pointer. Well, if you get to a branch statement and it says branch, if that flag is turned on, then it sets the instruction pointer someplace else and goes there. So an if statement in assembler would be do a bunch of stuff and branch if the flag is turned on. In looping, we would do a similar thing. We would say execute a bunch of instructions, and if the branch is turned on, branch back up and repeat those instructions. Branch back up and repeat the instructions until that flag is turned off, in which case we wouldn't branch back up there, we would keep going. Okay, so that's the primitive way to do it. Then we get these higher level languages, C, C++, C#, Java, Python, all these other instructions come along and they build upon that and just make it easier for us as programmers to do the same thing with nice high level statements like while, if. So that's where we are now. But underneath, it all comes back to the transistor, right? If we have power on these two things, boom, we get current.
Logic.
Logic.
And then count.
Yep.
Whether or not it stays legitimate during the whole source.
Yep. It's all scaffolded on top of these basic little building blocks that came out of these guys' work in the early 1900s. It's pretty cool. Okay, so now back to repetition. So thank you for my little digression there. Here's some common phrases you probably have, things like this said around you or by you or to you every day, right? Just normal English language stuff. Go down 3 blocks and turn left, right? I'm going to go 1 block. I'm going to go 2 blocks. I'm going to go 3 blocks. Oh, I've gone 3 blocks, so now I'm going to do something else. This is one I got a lot when I was a kid. While I'm gone, mow the yard. I always thought that was kind of interesting once I became a programmer because I was kind of a smart aleck, so I could see doing this if I was a programmer back then when I was a kid. So my dad says, hey, while I'm gone, mow the yard. So I start mowing the yard. So my dad leaves. He comes back. As soon as he's back, I turn the lawnmower off and go sit on the couch, right? Because he said, while I'm gone, mow the yard. Well, he's not gone anymore. So I guess I'm done. Yeah, I got grounded a lot, as you can probably imagine. And then I would hear this one too. Wait until your father gets on it. Anyway, but we're familiar with repetition. As we get into trying to write computer programs that integrate repetition, I just want you to always bring it back to the fact that you already know how repetition works. It's just like with the previous programs we've been writing. Your brain already knows how to process this stuff. We just need to figure out the puzzle of figuring out how to say it in Python so that it does what we know that the code needs to do, okay? So when it gets more complicated and gets tricky, don't get lost. Just come back to, wait, I know what this is supposed to do. I just have to figure out how to say it in Python. So here's an example of keep performing statements while a condition is true. While I'm gone, mow the yard kind of thing. Here's the form. Do while something. And this is where we're going to add our Boolean condition, true, false. Do while condition is true, right? We're going to have some list of statements. Maybe it's 2, maybe it's 20, right? But we're going to do a body of work here. And then we're going to end the loop. Go back up here. Anytime you see something like this, of course, again, this is pseudocode, but as soon as you see the end of the loop marked, you're always going to branch or jump or go to back up to the top of the loop and retest the condition, right? It's built to be a loop. It's built to keep repeating, okay? That's the general form. Here is another form. Okay, so this one, I would characterize this as a pretest. We're checking the condition as to whether to continue looping at the beginning of the loop. So this is a pretest, okay? As contrasted with the next one, which is a post-test. So the biggest distinction here, it's essentially the same thing, is we check at the end of the loop. So one thing to remember on this form is it's always going to execute the statements inside here once, and then check to see whether we're supposed to keep looping. So it does it once, and then says, while this condition is true, do it again, okay? So you could say, this is going to execute these statements 0 or more times. It may not ever execute these statements at all, 0 or more times. But this one is going to execute these statements 1 or more times, okay? And remember that as you're writing your code, because we'll ask this question, well, does it execute the code at all? Does it execute it once? Does it execute it 5 times? You know, you need to be aware of that, conscious of it. Here's another variation of it, but it's the same, right? It's the same as the first one. It's a pretest, but we changed the word while to until. And like we did with the if statements, all that does is flips this from true to false, right? Instead of while the condition is true, we're going to assume the condition's false, and we're going to keep looping until it becomes true. Okay, but other than that, it's the same. So we've got do while at the beginning, do until at the beginning. We've got do while at the end. We got do until at the end. So again, these are guaranteed to execute 1 or more times. And then we check until this condition becomes true at the end of the loop. And that's basically our 4 variations. Right? Pretty simple. That's about it. Now we do have the mid-loop test, which I'll talk about that in a little bit. I'll point that out when we get to it. But now we've seen the pre-loop test, the post-loop test, and then we've got the mid-loop test to come. Okay, so as we're looking at these problems, we want to continue to identify patterns, right? Whenever we see a pattern we're familiar with, we can say, oh, I already know how to solve that. I can go to my Rolodex and pull out a similar solution, boom, use that for the solution to this one, or at least as a starting point. Yeah, when we were dealing with selection, if statements, we realized that, wow, you know, some of these if statements have a particular pattern to them. Like if I'm checking, what was it? If I had one variable name that I was checking for a bunch of different values, and every one of my if statements was this variable, but with a different value, that, oh, I keep seeing that pattern over and over again. And so since it's so common, they gave us a specific pattern to make it easier to write that kind of selection statement. We've got the same thing with repetition. So a pattern in repeating algorithms, you'll want to remember this general pattern for how to implement it in Python, because you'll see enough of these things that you can use this as kind of a mental checklist for making sure you didn't forget something. Set an initial condition. Like sometimes you'll write a while statement that has this condition out here. It's like, oh, it's never running my code because I never set the initial condition. It doesn't know that it's supposed to start looping on it. So you're always going to have some kind of a setting of the initial condition. You're going to make your condition on a while statement. You're going to execute some, 1 to however many statements inside here. And then somewhere inside the loop, it's pretty much going to be common that you have to change whatever that condition was. You can't say X equals true while X, keep looping, but then you never change X. If you never set X to anything else, then you don't have any expectation that your loop's ever going to finish, right? And we have this problem in programming of writing code that has infinite loops in it. You've heard of that? Because they forget to put the statements in here. You're going to have at least one statement in here that changes what X could be the next time around, right? X may continue to be true for even a very long time, but eventually X has to change to false so that your loop can finish. So there's your pattern. You set whatever X is to some initial condition, you loop while X, you do some work in here, and then you change X at some point, whatever X is. X may be some big, huge, long condition with a bunch of ands and ors and nots and all kinds of stuff in it. But eventually, something inside that expression has to change, or you're going to loop forever. Yeah, and same with the other form. You set an initial condition, then you'll start looping, execute your statements, and then you'll change your condition. But realize on this one, we haven't even checked the condition yet. So you could execute the statements once, change the condition to false, and it just keeps going. It never does jump back up and execute these things again, because that's what the post test does, right? It assumes you're going to execute this stuff once, one or more times, and then this may be false the first time through and never repeat it a second time. Or it may be true and you keep repeating. Okay? So here's a little example. I want to dance until the cows come home. We as humans, we understand what that means. The initial condition, the cows are not home yet, right? We start looping until the cows come home. We execute the statements dance. We modify the loop condition. Somebody has to look out in the barn. Hey, did the cows come home yet? Yeah. And then we jump back up to the start of the loop. So this contains everything from my checklist before, right? Sets the initial condition, starts the loop. Here's our condition that we're going to check for. We execute some stuff, and we modify the condition somehow while we're looping, and then jump back up to the top. So silly example, but you get the point. This is how we're going to look at problems that were assigned and pick the repeating bits out of it. Okay, you told me to go read all the sensor data from a satellite. What's my initial condition? How long am I going to keep looping? How do I know I'm done looping? What work do I want to do while I'm looping? Right? Yeah.
Would you add extra instruction or detail into a loop if you're not getting a result? Or would it just set that loop and then alternate to a different loop? You're monitoring data from a satellite, but then you have some variables to keep in mind.
Yeah, it's a fair question to ask. If you're given an assignment, like maybe the satellite's supposed to tell you, hey, if I send you 999, that means I'm done. That means there's no more data coming. Or at the beginning of the satellite transmission, if it says, hey, I'm going to send you 100 packets. Okay, well, great. I'm going to set a counter to 100. And every time I get a packet, I'm going to subtract one from it. And as soon as my counter gets down to 0, I know, okay, I can stop. I'm going to stop looking for packets at that point. right? It's just part of the problem. You have to ask that. Now, if your boss comes and says, hey, I want you to process all the satellite data, write me a loop that receives it, and he doesn't tell you that it's going to end, it's a fair question to ask. Or maybe the answer is, oh, yeah, it never ends. You're just going to keep looping as far as until the thing falls out of orbit.
But like in an initial program where it makes sense, you need to start at the beginning and end.
Yep.
So,
yep. Exactly. You at least have to be conscious and look for, at this point. It's all going to depend on what the actual problem is. But the point I'm trying to make here is when you're looking at something and you're going to have to go write the Python to do it, you need to ask, okay, what is my initial condition? What is the work to be done? How am I going to change the condition during the loop? And when am I done looping? All right, so here's a little bit of pseudocode I typed up for you. So you've got an example of it, right? I created a variable. Cows came home yet is false. So I've set my initial condition. Keep looping while not cows came home yet. So I threw one of those little not things in there. It's a Boolean condition, so I can do that. Do while not the cows are home yet. It sounds a little awkward when we put it in Pythonese, but we're humans. We can adapt to that. We can understand what it's saying. Here's my work to be done. Here's me changing the loop condition. And then I hit this and I go back up to the top. Have the cows come home yet? Nope. Dance. Go look in the barn again. End the loop, go back up here. Have the cows come home yet? And on and on and on. Eventually the cows will be back in the barn. This will get set to true. Come back up here. Do while not true, which is false. We're supposed to keep looping while it's true, and it's not true anymore. So we immediately jump down here to line 10, and we're out of our loop. I don't want to be too pedantic about this, but I want to say it enough times that you get the repetition, you get the patterns that we're pointing out, because you're going to have to do this on your own. So here's another way of saying the same thing. Same initial condition. Cows home yet is false. Keep looping until cows came home. So I changed the while not to an until, just like we did with the if statements, right? Same thing. It's all the same except for that. So until this is the same as while not this. This is the main point there. There's another one. Setting our initial condition. Cows home yet is false. Start looping. Dance. Go look in the barn. Keep looping until cows came home yet. And what's the big difference with this one over the last two?
Equals?
No. Think about the work to be done. How many times am I going to dance? Since this is a post-loop test, I'm always going to dance once, right? With the previous ones, I may not dance at all. I may start the loop and the cows are already back home. They never left. They're home. So I never dance at all. But on this one, I'm guaranteed to dance at least once. Okay, here's a better example, hopefully, more along the lines of stuff that you might actually get assigned, right? Get a bunch of numbers from the user and print their sum. So we start thinking, what's my initial condition? Okay, so first time we've tackled a problem like this, so it may not be obvious. So my initial condition, I might include something else here. But it's not obvious from just looking at the user or looking at the question. But if you think about the sum, When I think about seeing something like that in the problem, I'm thinking, oh, I'm probably going to have a variable for that, right? So setting my initial condition is probably, if I think ahead a little bit, going to involve setting my sum to 0. Right? I'm going to start adding things to it. So I probably want to set the sum to 0. But we'll go with this for now. That's just me getting ahead of myself, but bear with me. So get the first number and putting it into a variable. Let's call it add in to be fancy, okay? Because it's better than X, right? So then we start our loop. How do we know where our loop is going to end? Well, that's a great question. How do we know when the loop's going to end? It just says get a bunch of numbers from the user. So just like with the satellite question, how do we know when that's ever going to end? So we're going to ask the question and probably artificially get some kind of an answer. If they don't tell us, we're going to build something like this. But let's do this. Let's say if the user enters -1, we'll consider that the end. We'll stop adding up numbers. Or 999. Although 999 is kind of dangerous because they may actually enter a number 999 and want us to add that up. So we got to clarify this. We got to ask some clarifying questions from our boss or from the teacher or whatever. How do we know we're done looping? And when we talk about numbers like this, special values in programming, we call those sentinels. So it's just a terminology thing. So a sentinel controlled loop is going to involve a sentinel, which in this case is some special value that we get from the user that tells us that we're at the end of the list of numbers that they want us to add up. So we're going to ask for a number. We're going to put it into add in. If it's -1, then we know we're done looping. So we are going to loop while the number we put in this variable is not equal to -1. And again, I'm doing this in pseudocode. You'll have to check me on this. If Python is !equals, or if it's less than, greater than, different languages do it different ways. But I'm meaning to say, huh? Okay, so Python is !equal. I'm meaning to say not equal to here, while add end is not equal to -1. But I'm going to keep looping. And here's something to remember. Don't ever also add your sentinel. Don't process the sentinel, okay? The sentinel is not meant to be added. It's not meant to be included in the work that you do. So whatever logic you implement has to realize that the sentinel value has been entered, but then not process it. So whether we do a pre-test or a post-test or a middle test, whatever, just remember, don't process your sentinel. It's bad form. Yeah, and then this is, I already mentioned that. Pick something for your sentinel value that by definition, you're just telling everybody up front, hey, don't enter that number. Typically what we would do is in our prompt message, we would say, please enter a number. And then in parentheses, we'd say -1 to finish, or -1 when you're done, something like that. But we tell them, hey, if you enter this special value, you're done. Besides, if you don't tell them, maybe they don't know what the sentinel is, or maybe they forgot, and then they're having to guess. Was it 0? Was it -1? Was it 999? What was the sentinel? And they keep entering numbers, trying to guess what the number was, and now their sum is all messed up. Okay, so it's good to put your sentinel value in your prompt message. Yeah, so the problem said to print the sum. So obviously we have to add each of the numbers. And we're going to use a variable. So our work to do in this case is basically add the number we got from the user to the sum variable. So like I said, I was thinking ahead a little bit. So going back up to the top, yeah, our initial condition, always set your, we call those accumulators or total variables, subtotal variables. You need to initialize those things as part of your initial condition if the problem that you're working on includes them. Sometimes it doesn't. So modifying the loop condition, we also have to do that inside the loop. And in this case, that's simply getting another number from the user. Give them another chance to enter something. We jump back to the start of the loop and we're done. Don't forget to print your answer at the end. We did all that work to ask for the numbers and add them to our sum. So after we exit the loop, make sure you print the sum. And of course, we can get into all the other peripheral things, what good pseudocode looks like for this kind of thing and all these different conditions, what the flow chart looks like, how to implement the Python. We'll do all that stuff. What test cases are good to include. You know, for our if statement programs, we talked about, oh, what would be a good value to try to test to see if we can mess up our program, to see if we can find a bug in it, right? Well, when we have repetition type things, it's how many should we enter? Okay, well, if I'm testing some sentinel controlled loop, I probably want to try entering the sentinel the first time. Never giving him any valid numbers. Enter the sentinel right off the bat, see what it does. Does it say 0? You never entered anything for me to add up, so I'm going to just report 0. Or does it add your sentinel to the sum and report -1? You know, it's a good thing to test for. So keep that in mind too. So with this problem, here's an example of what my pseudocode might look like. Initial conditions, set my sum to 0, get the first number, put it into my variable, and now I'm ready to go. Let me just start looping. While my variable is not my sentinel, I'm going to start looping. Add that variable to my sum variable, and then get the next number. I can reuse the same variable because after I do this, I'm done with that variable. So when I get the next number, I'm just going to use the same variable over again. No big deal. I get here and I automatically jump back up. It's kind of like chutes and ladders, right? I just slide back up here. I check and see if the next number they entered is my sentinel. If it's not, I add it to the sum. I get another one. Maybe that one's -1 this time. I'll go back up here. Oh, now it's -1. So now I'm going to stop looping. I jump down here and I print my sum. Now I'm done. Easy cheesy? I know it's really easy when I do it, right? Then I give you a couple of problems to do at home and it's like, wait, what did he say? Okay, so our checklist. Did we set our initial condition? Yes. Did we check for our sentinel value? Yes. Does the repetition work? Well, I guess it does. If I set my condition again somewhere inside the loop? Yes, I'm going to change the value of add-in, getting the next value from the user. So I changed my loop condition. And did I remember to do the stuff at the end after I exit the loop? Yes. And in this case, does our logic add the sentinel value to the sum? What do you think? Do I add -1 to the sum when they enter it? No. So excellent. Okay, here's another one. Slightly different. Hopefully you can see the differences here. Same thing. I set my initial condition, set the sum to 0, get the first number. I start looping. I add it to the sum, get the next number and put it into the add-in variable. And I loop until it's equal to -1. Boom, 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 a bunch of times. Finally, they enter -1. And I print my output. Okay. Do we set our initial condition? Yes. Same as this one. Do we check for the sentinel? Yep. I do the repetitive work. I set my condition inside the loop. Yep. Get next number, just like before. Do the stuff at the end. Yep, I did. Does our logic add the sentinel value to the sum?
Now, if you have a logic value and it becomes redundant, where it continually adds, well, equals the sentinel value,
Yeah.
will they be printed out in order of how it came into the sequence?
Well, we can rely from the beginning of the semester examples on these instructions getting executed in a prescribed order. It's always going to execute them in the order we think that they're going to, right? It's not just going to randomly jump around.
So in transmission, it would be through execution.
Yeah, yeah.
And then that's what would be the results.
Yeah, when you say things like, is it going to print it out? Well, the only print statement we have is here. So precisely, no, it's not going to print it out. We're just processing. We're just going, our little magic finger instruction pointer. We're going from one instruction to the next in a prescribed way until the logic happens to dictate we do something else.
Okay, so it won't become repetitive at that point, where you get numerous value, numerous occurrence of value.
If you try to do it, you can, yes. But that's why we're asking these questions of ourselves before we just go run it. Because infinite loop's bad.
Right.
But we're still the human, we still get to control it. We can break into it if we accidentally do a loop. Yeah. There was a time when computers weren't very good at that kind of thing. If you set up an infinite loop, maybe it would overheat and something would burn out, but they don't work that way anymore. Yeah. Okay, so again, this last question, does this logic add the sentinel value to the sum? Yeah, so that's bad, right? We don't like this implementation. We like this one better. This one's correct. Let's try a test case where we enter the sentinel the very first time we go through the program. Okay, we get the first number. We enter -1. Start the loop. Add -1 to the sum. Now our sum equals -1. Get the next number. Now it's like, why are you asking me for another number? I already gave you -1. I wanted to stop. So I enter 12. Okay, fine, 12. I get here and it says, oh, now I'm going to check the condition. But now add n is equal to 12. So I keep looping, right? I can do all kinds of weird stuff. This is not good. This is not correct. That's a bug, right? Yeah. Yeah, eventually we'll get there. Like I said, this is all conceptually. We're thinking pseudocode here. But yeah, all this can be done in Python. The problem with this is I can't talk about the post-loop tests because Python doesn't have a post-loop test. They don't have this blah, 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 and then check the condition at the end. Other languages like C#, Java, they do, but we don't really have that available to us here. Okay. Yeah, so we don't like this one, right? Oops. Yeah, so I already mentioned this. This is called sentinel controlled repetition because we have a sentinel value that controls our loop. Our loop condition is checking a variable for a specific sentinel value. And if that value is set to something, we won't continue looping. So it's sentinel controlled repetition. Sentinel is the end of the data stream. You can think of this stream of numbers we're asking for from the user to be a stream of data, right? Just terminology. Yeah. It's called indefinite repetition. So there's several kinds of repetition. There's definite, indefinite, and infinite. So this is indefinite because when we run this program, we don't know how many times it's going to run. The user is going to tell us how many times it's going to run, right? They may enter the sentinel the very first time. They may enter 100 numbers before they enter the sentinel, right? But they control how many times. So it's called indefinite repetition. Yeah, so beware of loops that never end. Usually when you hit an infinite loop, it's going to be because we forgot to modify the variable of our loop condition inside the loop. 9 times out of 10, that's going to be the reason. Called an infinite loop. So I mentioned definite, indefinite, and infinite. So whenever we forget to do something and it loops forever, it's called an infinite loop. And it's a very common mistake. But this is the point I want to point out here is it's not always a mistake. Sometimes we say while forever or while true, the word true, because we want our loop to run forever until told otherwise. So we design it to be an infinite loop. And then we have other ways of getting out of it later. But just, keep in mind, the computer is not going to get bored. That's the beauty of using a computer. It doesn't get tired of executing our loop. It'll keep doing it. Erase this byte from my hard drive and then erase the next one. And the next one, it'll wipe your whole hard drive, right? It doesn't get bored. It'll just keep going.
Very consistent.
Yeah. It does exactly what you tell it to, unfortunately. Okay, so let's look at this one. We set our sum to 0, we start the loop, we get a number again, put it into our variable, we add it to the sum, we keep looping. Boom, boom, boom. We keep looping. We never have any loop condition, right? So this is an infinite loop. So I will never print sum. There's no way for my instruction pointer to get out of this loop. I will never get here, okay, without intervention. But this is an interesting one, and you'll see this one in Python a lot. It's the same infinite loop, except that I added an instruction in here. Set the sum to 0, start the loop, get a number from the user, put it in my variable, and here in the middle, this is a mid-test, mid-loop test. If my variable has my sentinel value, then I break. And break is a special word in Python that says, whatever repeating structure that I'm inside right now, get out of it and go down here. That's specifically what it says to do. Break. Now, this works even if I'm inside nested loops. If I have an outer loop and an inner loop, and I come to a break statement, it gets me out of the inner loop and goes back to the outer loop. So I could still have an infinite loop in the outer loop, but this would break me out of the inner loop. Okay, so cool. I fixed my infinite loop. And this is actually a pretty clean pattern. You'll see this a lot in Python, where you say, basically you're saying while true, keep looping forever. Then I do some work, I check for my sentinel and break out of it. It's not considered purely structured programming. The people that are purists and like elegant looking code would call that unstructured. But hey, it works, and you'll see it a lot. Okay. So I'm coming back to this thing that I said at the beginning of the lecture where, there's special cases. There's certain patterns we look for in repetition, just like there were with the if statements and stuff, where we looked at the switch statement, case statement, where we found a special case. It happens so often, they provide an easier way to do the same thing, just as a convenience tool. We could do it the same old way, but this is easier for this particular case. It doesn't work in all cases. It just fits if you recognize this particular pattern. So that's the same thing here. All right, so there's a kind of loop. This is called a counter-controlled loop. So we had a sentinel controlled loop before. This is a counter-controlled loop. Why? Because we're going to set a counter variable to 0. We're going to base our loop based on this being less than some upper value. We're going to do some statements, and then we're going to add one to the counter. So similar to what I was saying before, maybe the satellite's supposed to send us 100 packets. So we start a counter at 100 and we start decrementing it. And when I get to 0, okay, I'm done with my loop. Same here, except I'm starting at 0 and counting until I get up to 10. Okay, this is a common pattern. So I'll show you the shortcut in just a minute, but you'll see this pattern a lot. I'd be surprised if you don't get an assignment where you have to implement this pattern with a counter of some sort. When I think about test cases for this, I don't have a sentinel value here, right? So I don't have to worry about that entering the sentinel value the first time or entering a few numbers and then the sentinel and checking to see if it added the sentinel to the sum. That goes away with this pattern, with this kind of a loop, right? But I have a new and more interesting kind of an issue to watch for. How many times is this going to loop? How many times am I going to execute these statements here? Now, this is known. I can figure this out. This is called definite repetition because I can figure out from just looking at the logic how many times it's going to execute. Is it going to execute once? Well, at least once, yeah. Is it going to execute 9 times, 10 times, 11 times? Okay, so I specifically wrote this logic to execute 10 times. And my counter value, each time that I get here, it's important to think about what the value of the counter variable is going to be at any point in time. The value of this is going to range from 0 to 9. Even though it's going to execute 10 times, it's not going to go 1 through 10. It's going to go 0 through 9. This is like one of those huge famous places where programmers make errors all the time. It's called the off by 1 error. Okay, knowing that we're starting at 0 and that we want to loop 10 times, some developers would say, I want you to loop from 0 to 9. So I'm going to say while counter is less than 9 because I want to go from 0 to 9. And that would be an off by 1 error because then it's not going to loop 10 times, it's going to loop 9 times. See, because of the 0 thing. We're either going to go 1 through 10, we're going to go through 0 through 9. And it's important to be conscious about that because guarantee you at some point, you will make an off by 1 error. You will not realize that this is not looping the number of times that you want it to. And it can be kind of insidious, especially at 2 in the morning when you're caffeinated and your brain's not working 100%. Okay, so we don't have the sentinel issue, but we do have the off by 1 thing to worry about here. But it does still follow the pattern we were talking about before. We set an initial condition, we check our conditional value, we do some work, we modify the loop condition, we repeat, and well, we didn't have anything here at the end, but okay, we didn't intend to, so that's all right. So whenever you see this particular counter-controlled repetition pattern in your problem, there's an easier way to do this, just to make it more convenient. This is the same thing, I just repeated it, is the same thing as this. Notice how much cleaner this is. So most programming languages have this ability to express it in this way. You just say, I want to do this many times. I want to use this variable, and I want you to start at 0 and go through 9. So it's going to loop 10 times. So all I did was I eliminated a couple of lines of code, right? This and this are both built into this kind. It's still doing exactly the same thing. And that's one of the biggest points I can make at this point is when you flowchart this, you're going to flowchart it exactly the same way as if you were doing this. So in your head, you just got to realize this is doing the exact same thing as this. This is just shorthand for it. Make sense? So this is setting an initial condition, int counter equals 0. It's doing some work. It's adding 1 to the counter every single time. And it's checking the condition to know when to stop looping. All the things that this does are built into this. It's just a more convenient way of writing it. And the great thing about this is we're being intentional. We know we're starting at 0, we're ending on 9. It's guaranteed to loop 10 times, and it's a lot easier. We don't have to do the math. We don't have to wrestle with ourselves. Do we have an off by 1 error? Okay? Fun stuff, huh? Yeah. Yeah, and this just says what I just said. Yeah, so terminology again, counter-controlled repetition. Some people might call it a counted do, counted for, counted do. And it's definite repetition because we know exactly, we can look at the logic and reason out exactly how many times it's going to loop. Yes. Here's another thing too. 0 and 9, there I have them as constants here, but I could say do counter equals min to max. They could be variable names. You could ask the user, hey, what number do you want me to start on and what number do you want me to finish on? You could put those values into these variables and you could loop from one variable to the other variable, right? It doesn't have to be numbers. It can be variables. We would still call that definite. This distinction is there. We know how many times it's going to loop upon entering the loop, right? Even though we still get those numbers from the user. From the loop's point of view, we know exactly how many times it's going to execute. Just because it's variables, it's still definite repetition. Okay, let's talk about how the flowchart is typed. And as I already said, the trick is to break it down into the actual statements being executed. Going back to, from the counted loop to the plain old loop, going back to selection, going back to sequence, going back to assembly language with the branch statements and the flags and the transistors and all that stuff. It's still doing the same thing under the covers, right? The flowchart still spells out exactly what the logic is, even if we're taking all these shortcuts and making the pseudocode or the Python look a little bit more elegant and clean. Okay, we're still setting an initial condition. That's probably going to be an assignment statement in a rectangle, right? Counter equals 0. We're going to check the loop condition. So that's going to be the diamond. We're going to have our conditional, X is less than 10 or counter is, less than 50, whatever. Number of satellite packs is less than 100. Whatever our loop condition is, it'll go inside the diamond. We'll check it. And then we're either going to go one way or the other. We're either going to keep looping or we're going to get out of the loop. The execution statements, the work that we're going to do inside the loop, of course, that's going to vary. We may have all kinds of boxes. Your entire program that you've written so far may go inside a loop, right? So whatever that program could have had in terms of the kinds and number of boxes, it could be a huge program inside the loop. But all that stuff will go inside there. Modifying a loop condition, we would technically represent that as an assignment statement with a rectangle again. And then we introduce this other thing. When I'm writing this on paper, I do this. If you're doing Flowgorithm, it's got a way that it's going to, it'll draw the line back around at the top kind of thing. But if I'm doing it on paper, I'll show, it's probably best to just show an example. Yeah, so here's an example of how I would do it on paper if I was doing it. So I set the counter to 0. I check to see if my loop condition is met. Yes. I do the statements, do the work. I modify the loop condition. And then this is the little circle like I use where I just jump from down here back up to here. I could draw the line. But like when I learned to flowchart, they expected certain, it was almost like government regulations or something, the way they expected us to do our flowcharts back then. But they said basically there was a rule, all arrows can only go to the right or down for whatever reason. But if my arrow can only go down, that means I can't draw it back upwards. So I have to draw it down to a jump circle and then back up here and then I can go to the right from that circle. But so we don't have to do that. We can get away with that a little bit. I'm not going to be that rigorous with you, but Flowgorithm will do it however it wants to.
Formatting.
Yeah, it's pretty good. I mean, they'll use different color boxes than I've used here, right? Yeah, but generally that would work. And then, like I said, the entire programs you've written so far might get glommed right in here. So this could get crazy. This could go all kinds of different directions, if statements and all kinds of stuff. Maybe other loops inside there. But that loop right there, that's how you would flowchart it. Okay, so here's the other kind where we do the post loop test. All we're doing is we're moving the diamond down to the bottom, right? We'll go back up. Okay? But it's still just rectangles and diamonds. We're not introducing anything new. It's just exactly what the code is going to do.
Those are what defines the statement, what the assignment of the statement, that the command of the statement.
Yeah, exactly. It's really easy to think, oh, this is getting complicated. I'm getting, 6, 8 instructions. It's getting really bizarre. It's really, we're only incrementally making it more complex than the last assignment that you did. So it's really not that much more. So don't let it make you think that you're getting blown away here. All right, another example. Hopefully you guys are still with me. Ask the user to enter their name to play. If they enter their name, display the message, let's play, and their name. Keep repeating the question until the user enters the word quit. Now, that's not a very interesting problem, right? But I'm keeping it intentionally easy and focusing on the loop part, not what we're doing inside the loop on purpose. So let's look at some examples of how we would implement that. So let's think about this one. Pseudocode again, right? So get a name from the user. So I've set my initial condition while the name that they entered is not quit. And, this is pseudocode. So I'd probably be saying, get the name from the user and put it into a variable called username. I don't know, whatever. So when I say while the name they entered, I'd probably be referring to the variable name. Well, that's not equal to the word quit. Then I keep going. I display my message, and then I get another name from the user. Okay, we played. Let me get another name. Loop until they enter quit, and then I stop looping. So you're going to see this a lot because from now on, even if it's a simple problem like we've been doing, like, hey, add these things up and calculate them, or calculate the discretionary income based on these wages, whatever, I'm probably going to start adding, keep doing it until they enter quit. That way you can wrap the whole program inside this logic that says just keep going. Makes it a lot easier to test your code too, because instead of having to run your program every time, it'll just keep repeating until you enter your Sentinel value, and then it'll stop. And I think the book introduced that a while, so I've been kind of ignoring that for a while until we got to the repetition part. So you might have already seen it if you're reading the book. Okay, how about this one? This one works just as well, right? We would call this a mid-loop test, right? So while forever, until the sun explodes, right? While forever. Get a name from the user. If it's not equal to quit, or if it is equal to quit, break. If it's not, then we display our message, and we go around again. I could keep giving you lots and lots of examples of showing you how to break down the problem and do these same patterns over and over, but hopefully at some point you'll be like, okay, I got it. That's excellent. Because then when I give you the hard problem, it's like, yeah, I already know the structure it's going to take. It's going to be either the pre-loop test or the mid-loop test or whatever, and you're just going to spit it out because you've already seen it several times. Okay, what's different about this one? Oh, here we go. Set go, a variable equal to true. While go, and I think I made this point earlier that if you can understand this concept that you set the value of a variable so that later you can use that value or test that value later, the ability to have that thought process in your head will give you a lot of mileage later because you will use that a lot in programming. Okay, so get the name from the user. If the name equals quit, now we're going to set the variable to false. Okay, so our initial condition, we've modified our condition. We go around and we're going to check it again. So everything fits, right? Set initial condition, test it, change it. All those things are present. But essentially, it's doing the same thing as before. This is also where, hey, there's many ways to skin a cat. You all are becoming artists, right? So far, I've been teaching you, here's how you use this paintbrush. Here's how you use the color pink. Here's how you make this kind of a brush stroke on the canvas. But you've got a blank canvas sitting there. You can paint it any way you want to, as long as the logic works, okay? Here's another one. Set the message equal to blank. I'm doing it a different way, right? Set the message equal to blank. Display the message, huh? Well, the message is blank, so I don't have a message. Okay, whatever. Get a name from the user. Set the message equal to let's play and the name they entered. And keep going until name equals quit. Does that do what we want it to? Okay, what's wrong with it? What's the bug, did you see?
Yeah, I mean, it's the same thing. Added to
yeah, other than at the beginning of it, it's going to display a blank message.
Right.
Other than that, it kind of sort of works, doesn't it? And I will see lots and lots of different things that you guys do, crazy stuff, and I'm going to be sitting there scratching my head saying, why did they print a blank line at the beginning and then they do exactly the right thing from then on? It's like,
if statement.
Oh, well. Yeah. You could put an if statement around this that says, if the message is not blank, then display the message. That would fix it. But we're adding more and more lines of code. There used to be this joke about Visual Basic programmers, that the way the Visual Basic programmers debug their code is they keep deleting lines of code until it works. The message there being that Visual Basic by its nature was very wordy. It was almost COBOL-like. And you would end up writing lots and lots of code to do something fairly simple. And usually one of the bugs you would have if your program wasn't working right is you added way too many statements to do something that could be done a lot easier. So you just keep deleting code until your program works. So just a joke. Okay, a couple of other examples we could go through. And again, we haven't done any of this in Python yet. In a way, I'm assuming that based on just the conceptual discussion of this and the book, you've seen in the book the actual Python syntax that it uses. So I could write the Python up here. I could do the pseudocode for you. I could do the flow chart. But at some point, I would really love it if you would take the concept and be able to apply it. So I'm not going to give you the Python right now. We'll show some examples next time. But I want you guys to try to do this program looking up what the syntax is for how you want to implement the pattern. Because if you know what the pattern is and you can do the pseudocode for it, that translates pretty easily into the Python. And I'll just tell you, you're not going to use the post-test pattern in your code, because again, Python doesn't have one of those. They don't have a do ... until. They have the checking the condition at the top, or have the checking the condition in the middle and then breaking. They have those patterns. So don't even look for the other one. But like this one, if you've looked in Canvas, this is the actual assignment this week. So I'm not going to do that for you yet. We'll walk through some of that next time if you're having trouble with it. But this is exactly the kind of problems that you could anticipate getting. Okay, ask the user to enter numbers until the user enters 0, and then add up the numbers and display the sum and the average. Now we've added an average in there. Okay, let's see. What would that look like? What is my set initial condition going to be here? Okay, I'm going to have a number variable. What am I going to set it to initially? Okay, I'll go with it. Any other initial conditions? This is similar to the previous example, so I'm pretty sure I'm going to have a sum variable. I'm going to set that to 0 up front, right? I mean, this is a debated thing too. Back in my early career, it was like a religion. You always set variables to a value before you use them. You'll even get called on stuff now. I mean, Flowgorithm gives you a big hairy error if you don't declare the variable. So, early on, I mean, it goes back to like in the silicon, you're dealing with memory that's sitting on a piece of silicon. There is no initial value set. It's just randomly whatever the state of the electrons was when it powered up, right? But then at some point, I can remember the version of a Microsoft compiler that came out. And the way it worked is when you wrote a program and you declared a variable, it guaranteed to you that that variable was going to be set to a default value of 0. There was a really good reason for it at the time, and it goes to security, because if you're dealing with a program and it's looking at whatever the memory happened to contain before, what if that memory is the same memory where your social security number was sitting before? Okay, well, there's certain conditions that can be exploited by somebody, a programmer that knows what they're doing. And so it became very important to stop letting that happen. And programs started saying, no, we're going to just write this compiler so that it initializes all the variables to 0. So you can't see what the data was contained there before, for privacy, for security. Okay, that's why it happened. But in my head, it was pounded into me, and I'm going to pass that on to you. Never assume what your variables are. Always be intentional about it. If you declare a variable, set it to you what you want it to be initially set to. So if I know I'm going to use a sum variable, I'm not just going to declare it and start adding stuff to it. I'm always going to just consciously in my head, okay, I want to set that to 0 intentionally. That's why I always go to that pattern. Okay. Yeah.
Aren't we going to need to like have a counter or something as well?
You're thinking ahead to the average, aren't you? If I'm going to calculate the average, yeah, I'm going to have to do extra stuff. What do I need if I'm going to calculate the average of a bunch of numbers? I need 2 things, right? I need the sum, which I'm already going to have that. What else do I need?
How many numbers?
The count. I need to know how many numbers were entered. Very good. So I'm going to also declare a variable and set it to 0. Okay. All right, so that's my initial conditions. So let's say while what? While I guess I need to do something else here, don't I? So I said set number to 0, but do I want it to be set to 0? Yeah, I think what I want to do is get a number from user and store into number, right? That's the initial condition for number. That way I can check my sentinel. I'll even put here in my comment, sentinel, while number is not equal to, what did we say our sentinel was? Until the user enters 0. So while number is not equal to 0, right? And I want to keep looping. Okay, so I'm going to do something inside this loop. One thing is going to be do some work, right? But then I want to also change my loop condition variable. How am I going to do that? I got to do something to number, right? What am I going to do? How about get another number from user, right? That would change it. So now I've got a basic loop. I'm not doing anything in here, but I'm looping, 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 looping. Finally, the user enters 0, and boom, I jump out of my loop. Okay, so now I got to do some work. Well, I know from the previous example that I want to add whatever they entered to my sum, right? Everybody remember that that format of a statement? So I could say add number to sum, right? But how do I do that? I basically want to add number to sum and then store that back in sum, right? This is kind of confusing, you know, it was to me at least initially when I started reading assignment statements, because it goes back to our semester-long comparison between programming and math, right? In math, I'd be saying, wait a minute, sum equals sum plus number. There's no way that those can be equal, right? But that's not what we're saying here. When I type in a statement like that in Python, I'm saying, calculate what's on the right side of the equal sign. And once you have the answer, store it into whatever's on the left side of the equal sign, right? So that's why I read this in my head now. Calculate sum plus number. And once I have the answer, store it into sum. So that's how I add number to sum. So I say sum equals sum plus number. So now I've got a functioning loop. And when I get down here at the bottom, I say print sum. Good, got my output. But I'm still missing the average. So at some point I want to say print average, right? But I don't have average yet. I probably want to do some kind of calculate average. And we said a minute ago that I calculate the average by dividing the sum divided by we put it up here, right? Count. But I haven't done anything with count. So as far as I know, count's still going to be 0. What I want count to be is the number of numbers that the user entered, right? So what do I need to do to this to make this the number of numbers that they entered. This is where it comes to the puzzle solving side of programming. I know I need the count. How do I get the count? Right? If this loop loops 5 times, I got 5 numbers and added 5 numbers to sum, then I know that the stuff inside this loop executed 5 times. So if I could just do something inside this loop so that when I left the loop, count contained the value 5, how about that? So every time through the loop, I'm going to add 1 to count, right? So that's the same thing as saying add 1 to count, right? Count equals count plus 1. What do you think? Does that have a chance of working? Probably. Okay, I'd really like to give you a helper. You know, we've talked about this with some of the if statement stuff and earlier, but it's desk checking, right? Have you ever heard people talk about, you know, how do you remember stuff, right? I know as teachers, they kind of drill this into us that if you really want every person in your class to remember something, you will show them a picture of it. You will say it out loud for them. You will give them a book where they can read it. Make them write it down. Make them tell somebody else. And by doing all those things, you're hitting all of those different little learning styles, modalities, and you make all these different neural connections. It's like coming at the exact same piece of information a whole bunch of different ways and different times, different contexts. They might even say, hey, while you're thinking about this, sniff a scent. And then anytime you smell that scent, it's going to be connected to that piece of information, right? Just all these different ways of creating these neural connections. Well, along those lines, desk checking is really important. So I encourage you to do this, even though it seems kind of like it's a hassle, it goes out of the way. If you really want to understand the logic of your program and why it's working and why it's not working, just use your finger as your magic instruction pointer and walk from instruction to instruction. And the way we desk check is we write down the value of all of our variables, or the name of all of our variables at the top, sum, count, number. I guess we've also got average. Right? You just write all these variables up here and you pretend to be the computer. Okay, first instruction, set sum to 0. 0. Set count to 0. 0. Get a number from the user and store into number. Okay, whatever. 3. While number is not equal to 0. Is number not equal to 0? Mm-hmm. Yes, so that's true. So we will continue looping or start looping. Do some work. Sum equals sum plus number. So sum plus number is 3. And we want to store that back into 3. So now sum has the value 3 in it. So you see I'm walking through the code and I'm manually editing these variables. Next one, count equals count plus 1. Get another number from user. 12. And loop, jump back up. Is number equal to 0? Not equal to 0? Yes, it's not equal to 0. So I keep looping. Sum equals sum plus number. Count equals count plus 1. Get another number from user. Okay, I won't keep going. I'll enter 0 now. And loop, go back up to the top. Is number not equal to 0? No, it's equal to 0. So this is false. So I don't continue looping. I jump down to here. Calculate the average equals the sum divided by count. Average, 15 divided by 2. So I'm going to float value for that. And, oh, I wanted to tell you guys this other operator that Python has that I haven't told you about. You probably saw it in the book, but remember we did that assignment where we had the modulus operator, and that was kind of cool, the remainder. A lot of people have never come across that. Well, 15 divided by 2, 15 slash 2 is a float, and it's 7.5, right? Easy cheesy. But if you say 15 slash 2, that's kind of a cool operator in Python. It's basically called the floor division. So this returns an integer. I know some of you were playing around with the round function, where you can round a value to the nearest integer kind of thing. Well, you don't have to if you use the slash operator, because 15 slash 2 is just 7. There's no decimal. It returns an integer. So anyway, doesn't have anything to do with this assignment, but I thought I'd throw that out there as trivia. But yeah, 15 divided by 2, we get 7.5. All right. Then we say print sum. So we've got our little computer screen here. What does sum have in it? Sum has 15. We're going to print that. And then we're going to print average. Okay. So by walking through the code, manually desk checking, I now understand exactly what's going on inside my program. And I can verify without even having a computer that my logic is right and it's doing the right thing. Now, of course, if you do the math wrong, we humans aren't perfect. That's why we're trying to get computers to do this work for us. If you do the math wrong, funny story, I had a computer science degree. So my bachelor's degree is basically a math degree with a few computer classes thrown in, because this was back in the olden days. But that was my big problem. I would be taking advanced calculus and, it's like, oh, wow, that's cool. Area under a curve and, differentials and integrals and all this kind of stuff. And it's like, yeah, I can understand exactly what they're saying there. But then I would add 3 plus 2 wrong and get the whole assignment wrong. So I could do the really hard stuff. And then the math, the simple arithmetic is where I would screw up. And so that's why my GPA sucks. Anyway, it's all good. All right. So you've seen the pseudocode for that problem. You've seen the desk checking. Don't even need to implement it in Python. It works, right? We already know that. Whatever programming language we decide to implement this in, we already know it works. Okay? All right. So I've got other examples and stuff that I could go through that you're going to see stuff like this. Here's a fun one. Each day a weather station receives temperature data in degrees Fahrenheit. There are 15 remote sensors reporting this data. Ooh, 15. They told us how many sensors there are. That's starting to feel like maybe it's going to be definite repetition. A program is to be written that accepts 15 Fahrenheit temperatures, converts them to Celsius, and display each temperature to the screen. After the temperatures have been processed, it should display all temperatures processed on the screen. Okay, so I could go through the same exact long drawn out exercise here, right? And we could pick out the repetition bits out of the problem. I could implement it in 2 or 3 different ways: pre-test, mid-test, post-test. We could desk check it and prove to ourselves that it works. But we'll do that next class. So I want you to just kind of think about this. See if you can scribble down on paper how you think you would do this and come back next time and we'll work that together in class, okay? But it looks like a big long paragraph of junk, but hopefully by now you can see, this is not that bad. I can tell by the 15 that it's probably going to be a counter-controlled loop, right? So, but you can start kind of seeing the pieces and seeing the patterns, hopefully. So, did we hit everything? While, for, in, break, sentinels, counters, lots of stuff. I even talked about an operator we hadn't seen before. Doing the same old stuff we've been doing with Boolean expressions. You know, we're using less than, greater than sometimes in our expressions now for the counter stuff, but you know, it's all Boolean, good stuff. Yeah, and remember again, we can nest these things. We'll try to do an example next class too of a nested loop. Show you an example of how to detect that in the problem. Oh, we're probably going to have a loop within a loop, and what does that look like? Flow charts, counter controlled, sentinel controlled, definite, indefinite, infinite, pre-test, mid-test, post-test. Yep, we talked about all this stuff. Just a hint of some more stuff to come. Like I mentioned earlier, Python has this thing called a range function. And it's sort of kind of like a helper, like the counter-controlled loops. If you create a range in Python, you can give it a beginning and an ending value, and it'll just create a collection of all of those things that you can repeat over. It's kind of cool. We'll talk about that. There's also these things, when we were talking about the data type stuff, you know, a month ago, we talked about lists, objects, stuff like that. Well, these lists are kind of cool because they come with the built-in ability to say, hey, I want you to do some work for every item in that list. You don't have to write your loop logic. It'll just automatically do it for every item in the list for you. So that's kind of cool too. Streams, kind of hinted about that stream idea. You can kind of conceptually think of all of these pieces of data that you're going to loop over as a stream of items. Well, we actually have these things called streams. Like if you're going to open up a file and you're going to read every byte in the file, or you're going to read every line in the file, that's called a stream. And so you've got ways you can loop over a stream in Python. Okay. Yeah, and we'll talk about that kind of stuff later. But I think this is enough of a fire hose for tonight, so didn't want to get into too many of those things. Okay, anything? Any questiones? Okay, well, the assignment should be out there on Canvas. So have fun with it. Like I said, all the Python equivalents of this are right there in the book. So hopefully you won't have any problem at this point getting the syntax examples and taking your pseudocode and turning it into Python. But again, don't worry about it if you can't. Just come back next time. We'll go through it. Okay. All right. Thank you.
Thank you.